Welcome, everybody. It is a great pleasure to me to introduce Ilka Agricola. She is from the University of Marburg, and today she's going to speak about 3 alpha delta Sasaki manifold. Thank you very much for accepting this invitation, Ilka. It's a pleasure for us.
Thank you for the invitation, and yeah, I hope there will be some opportunity to visit you in real, not too far in the future at some opportunity. It was a pleasure to be in Córdoba, and I'm really looking forward for big travels again. So this is going to be an introduction to 3 alpha delta Sasaki manifolds, and I do not assume, of course, that you know what that is. The goal of the talk is rather to introduce you to this very rich new class of manifolds, to give you a survey and ideas why these are an interesting playground and what you can do with them. So I hope at the end you will be convinced that they're nice objects. And maybe you will find applications in your daily work. All this is part of a longer ongoing project I started some years ago with Giulia Di Leo from the University of Bari. And lately, my PhD student, Leander Stecker, joined in. So that's why he's written here with affiliation Marburg. But actually, on the 1st of October, he started working in Hamburg. So that's the fate, you know, you educate good students and then they leave you. That's how it is. Okay, so what is all the business around? So all this is in the realm of free contact geometry. So let us just look back a little bit. In the 60s, Sasaki introduced what we know now by Sasakian manifolds. And relatively quickly afterwards, 1970, Courant and Driste realized that this is a very natural definition to assume that you have 3 orthogonal Sasaki manifolds. And the quickest way to see what a free Sasaki manifold is, this is a manifold of dimension 4n plus 3 with a Riemannian metric, such that the metric cone you construct over it has holonomy inside SPn plus 1, meaning just that it's hyperkähler. There are a few consequences from these properties. For example, you have topological consequences. Such manifolds always have odd Betti number up to middle dimension. They are divisible. No, the odd Betti numbers up to the middle dimension are divisible by 4. The structure group is inside SPn, which corresponds to the 4n dimensions and the identity in the 3 other dimensions. It's automatically a spin manifold. They are Einstein. The classical quaternionic Hopf vibration is actually the role model of such a geometry as 7 with that vibration. And there is a deep relation to quaternionic Kähler manifolds, which actually will play a big role in this talk. A manifold in dimension 4n plus 3 is free Sasakian if and only if it admits 3 killing spinors. Now we saw above that it has to be a spin manifold, so having good spinorial properties is not that surprising. And you know that I love spin geometry, so this is a hint that there's some deep connection going on. There are many examples known, many inhomogeneous examples, but in particular, there's also a classification of the homogeneous case. If you recall Berger's holonomy theorem, then you realize that contact manifolds do not appear in this theorem. The reason being that the Levi-Civita connection is not adapted to the investigation of contact manifolds. Main reason is that the holonomy representation is never irreducible, but that's the assumption in Berger's theorem. Okay, so what's the outline of this talk? Well, so first I will say something about the context, the geometry of almost free contact metric manifolds. Then we will introduce you to this new class of objects. Then the whole philosophy is if these are good geometries, then there should be good connections. So the connection will be called the canonical connection. We will say something about that. We will prove that 3 alpha delta Sasaki manifolds always have, in a canonical way, a submersion over a quaternionic Kähler space. Then we will say a lot about the homogeneous space, and I hope that time will allow to also say something about curvature operators in order to give you different directions from where you can go on from this class of objects. And obviously, if I'm going too fast, the internet breaks down or anything else happens, or just a question or a comment, stop me, please. I don't see anybody, right? Okay, so almost contact metric manifolds. Just in a nutshell, these are odd-dimensional manifolds, and you have a preferred direction psi, the Reb vector field, the Riemannian metric, and dual to xi is a one-form eta. And in the orthogonal complement of the line spanned by xi, you have an almost complex structure phi, right? And this is indicated by this rotation, just as a normal almost complex structure would do. And on the border of my square of this plane, I'm just indicating the sense of rotation. So we have eta, we have this phi, and then the structure group of such a manifold is automatically reducible to UN times 1. There is a fundamental 2 form associated with the almost complex structure phi, which will be called big phi. There's an integrability condition for this almost complex structure, which is measured by a Nienhaus type tensor, which is called n phi. And the manifold is called not integrable but normal if this tensor vanishes. And alpha Sasaki is now a condition on linking basically the two forms one has, namely on one side the differential of eta, and on the other side the fundamental 2 form. Okay, so in the alpha Sasaki case, I require that these two are proportional, and furthermore that the structure is normal, so the most as integrable as possible. In fact, if I assume these 2 conditions, then the Reb vector field is automatically a killing vector field, and the Sasaki manifold is just realized by the case that the constant alpha is equal to 1. Because why is it reasonable to talk about alpha Sasaki instead of normal Sasaki? Well, if you rescale a metric G, a Sasaki metric G, by a constant, it doesn't stay Sasaki. Actually, rescaling by constants leads naturally to alpha Sasaki, and that's why we include this case immediately. Otherwise, we have a normalization condition which we drag along, which is not really necessary. Okay, now almost contact free manifolds. As I said, this would be something on dimensions of dimension 4 and plus 3, which has to deal with free orthogonal almost contact structures. So we have the free 1 forms and with dual vector fields and the corresponding almost complex structures. And the idea is, now this is what I'm drawing here is the vertical space. The vertical space is just what is spanned by these 3 vector fields, xi1, xi2, xi3. The horizontal space is everything else, which is not drawn on this picture. And now schematically, now where I have these 3 orthogonal vector fields, Reb vector fields, right? For each one, I have an almost complex structure rotating in the orthogonal plane. So these are the 3 planes which are tried to draw here. Each one is an almost contact metric structure. The horizontal space goes away. And now the compatibility conditions are exactly those which you can read from the picture. So for example, the orientation between xi1, xi2, and xi3 is chosen in such a way that xi1 times xi2 equals xi3 in the 3-dimensional subspace. Phi1 composed with phi2, so this would be phi1 composed with phi2 is equal to phi3. And the image of, for example, xi2 under psi1 is phi1 is xi3. Now, if you go to xi2, this is here. I want the image under phi1, which is this one. So I end up in xi3, which is the case. And that's why the picture puts all the compatibility conditions together in one notation instead of dealing with all that. The structure group is then SPN times identity. Okay, the manifold is said to be hypernormal if all 3 almost contact structures are normal, right? So integrable as we remember. And then, now this is a very general definition, then there are some remarkable classes, namely, for example, free alpha Sasaki would be just that each of these single structures is Sasaki. Observe that actually such manifolds are automatically Einstein, or if it's called free co-symplectic, if each of the structures is co-symplectic, free quasi-Sasaki, if each of the structures is quasi-Sasaki, right? And so you get a bunch of classes. However, let's observe the following crucial thing. All these new classes do not postulate or require any kind of relative behavior of the three single structures, right? I'm just assuming that each single structure has the same property. And this is, in fact, something we are going to give up. So this we are going to change, okay? And now, a theorem by Kashiwara, which is actually quite surprising, is that if you require the contact condition, d eta I equals 2 phi I, then the manifold is automatically hypernormal and therefore free Sasakian, which for almost contact manifolds in dimension 2n+1 is totally wrong, right? And so try to remember this condition, because this is the condition we're going to play with in a few minutes. Okay. Now there's another object which comes along with every almost contact-free manifold. It's the so-called associated sphere of almost contact metric structures. Because if you take your free Reb vector fields, xi1, xi2, and xi3, obviously these are just three orthogonal vectors on a sphere of vectors of length 1. So I get a sphere S2 of structures where I see quickly that for any vector A on the sphere, the linear combination of the phi i's corresponding to the vector, which just yields that I take the corresponding linear combination of my three orthogonal Reb vector fields, will define, again, an almost contact metric structure. So every vector psi on this sphere has an associated almost contact structure, right? And now the point is, let me have a sip of tea. That all these structures play a role, right? It makes sense to look at them. And for example, in 2016, so relatively recently, Capelletti, Montano, De Nicola, and Yudin proved that if the three almost Reb vector fields, okay, or the three almost contact structures you start with are normal, then in fact, this is going to be true for all associated structures on that sphere. Very useful. Unfortunately, for our applications, we will not need the situation that the Nyhan-Horst tensors are vanishing, but we need that they are skew-symmetric. And we need this skew-symmetry in two different flavors, namely, first flavor is skew-symmetric when restricted to H, and skew-symmetric on the whole tangent space. And what we proved is that the same conclusion holds. If this is true for the three fundamental almost complex structures, then it's true for all almost complex structures in this associated sphere. So we see that the sphere somehow inherits the properties of the three structures you started with. Good. Now let's jump to this new class of free alpha delta Sasaki manifolds. So first, for the notation, so free alpha Sasaki, this is a generalization of free alpha Sasaki manifolds. That's why the alpha stays there. But instead of having one constant, I now have two constants. So a free alpha delta Sasaki manifold is an almost contact metric manifold, just as defined before, satisfying first, here is the free alpha Sasaki condition. And now comes an additional term which vanishes in the free alpha Sasaki case, which now links the one forms coming from the three different Reb vector fields, right? Because here's a term which is added is eta j wedge eta k, where I, j, k are just an even permutation of 1, 2, 3. So d eta 1 has now not only a phi1 contribution, but only a eta2 wedge eta3 contribution. And if alpha is equal to delta, of course, this vanishes. The constants alpha and delta, one sees quickly, alpha is not allowed to be 0, but delta is. If alpha is equal to delta, we will cover the free alpha Sasaki case. If we have a look at condition 1, we see that only the free alpha Sasaki case is one where the phi i's are closed. In general, they're not, right? Because I have this delta minus alpha factor here. And in fact, we will see quickly that it is very reasonable to distinguish three classes of these manifolds. We call them positive if the product alpha times delta is positive, negative if this product is negative, and degenerate, guess what, when delta is equal to 0, which is the only way how the product can be 0. Okay, in many things we will see that this is the right distinction. But first, let's give a very easy justification for this distinction. It comes from homophatic deformations, right? So,
Ilka?
Yeah.
Hi. So it doesn't matter if delta is greater or smaller than alpha.
For the moment, it doesn't, but there will be situations where these things play a role. But yes, the sign is not a crucial, the sign of the difference is not a crucial quantity. It's really the product.
Okay, thanks.
And also, so if they're positive, you may as well take both positive. Because if both are negative, then you can bring it back to the case where both are positive.
Okay, great.
Right? Okay. So here's a very natural class of homophatic deformations of any free almost contact metric structure. You rescale the one forms by a constancy. Then, of course, the Rib vector fields rescale by the inverse constant. You leave the almost complex structures unchanged. And the new metric is something in one part and something in the horizontal part and an addition of the eta I wedge eta or eta I tensor eta I in the vertical part. And then you have to check that this really has to be compatible, and the compatibility condition is such an equation, and this has to be positive, of course. Okay. Now, if you start with an free alpha delta Sasaki manifold with constants alpha and delta and perform such a homophatic deformation, then it will again be alpha delta Sasaki, free alpha delta Sasaki with new constants alpha prime and delta prime, and these constants are computed by these two equations. In particular, we see the sign of, now let's try to switch, right? If I take the product of alpha prime times delta prime, okay, this is going to be alpha, delta, C goes away, and A has to be positive. So the upshot is that if the product was positive, then it's positive afterwards. If it was degenerate, it's degenerate afterwards. And if it's negative, then it stays negative. So the class is preserved, and in the non-degenerate class, the sign is preserved. And now, why does this yield a good classification schema? Very rough, of course, for these manifolds. Well, the positive case, so positive free alpha delta Sasaki manifolds, are exactly those which admit a homophatic deformation to just a normal free Sasaki manifold, meaning alpha delta equal to 1. Similarly, alpha delta negative is homophatic to, well, the analog of this condition is alpha minus 1 and delta equal 1. We will see in a minute what kind of manifolds these are. Right? So this gives us a first hint. In particular, we see that the negative case cannot be recovered from free Sasaki manifolds. So we really have more manifolds. Here comes a degenerate example to see that this happens really. So the role model for the degenerate case is the Quaternionic Heisenberg group. Now, I put down everything here, but this is just to say that things are explicit. You're not supposed to read all the indices now. So this is the simply connected Lie group with Lie algebra Gn, which has 3 vector fields. And then I will have tau Rn plus n, Rn plus R2 n plus R3 n plus R, where R goes from 1 to n. Here are the commutators. I make the commutators depend on the positive constant lambda, which just appears right in these places. And then here's a wrong index. This should be an n and not a p. You define in a very natural way almost contact structures. And in particular, G lambda is the Riemannian metric such that the vectors you started with are orthonormal. And then you compute what the derivative or the differential d eta i's are. And you get d eta I is lambda times phi I plus this contribution eta j wedge eta k. So if you identify parameters, you see that lambda just is up to constant this parameter alpha, and delta is equal to 0. Oops, no, I jumped somewhere here, right? Okay, so we have degenerate examples, and in fact, the Quaternionic Heisenberg group, it's not written on the slide, but the Quaternionic Heisenberg group with these structures is a naturally reductive space. So in fact, this structure comes really from an underlying structure which will be of interest later on. Here let's construct some negative non-degenerate examples. This is going to happen from Konishi bundles. So start with a quaternionic.
Ilka, in the Heisenberg example, it looks like the metric G is the canonical one. I mean the H-type metric. And what about the deformation? You get really new metrics or with the H deformation?
No, it stays degenerate. So you just rescale lambda. It doesn't matter.
So the metric is the same with the deformation, essentially.
Yes. Yeah.
Okay.
You don't gain anything from doing the H deformation here.
Okay.
And indeed, the degenerate case is the case about which we have the least to say. So I will speak a lot about the positive and negative case. And the degenerate case is still mysterious because we have some structure theorems for them, and it's not so clear whether there are really many interesting examples. Okay.
Yes.
So, let me put it the other way around. It's definitely clear that positive and negative are extremely rich classes. So we looked at these first. Right? Okay, so start with a quaternionic, not hyperkähler, quaternionic Kähler, not hyperkähler manifold, scalar curvature different from 0. Then we have the canonically associated principal SO3 bundle. And it is well known that if the scalar curvature of the base is positive, this is a Free-Sasaki manifold. And if the scalar curvature is negative, then this SO3 bundle has a so-called negative Free-Sasaki structure. Okay. And now what is a negative Free-Sasaki? Well, negative Free-Sasaki is normal almost free contact as usually, but the metric is not Riemannian anymore, but it's semi-Riemannian. And in fact, the signature is adapted to the splitting in horizontal and vertical space because it has signature 3,4n. And beside that, everything looks like in the Free-Sasaki case. And now if you take such a negative Free-Sasaki manifold and we scale the metric in a clever way such that it becomes a Riemannian manifold, Riemannian metric, then this is exactly a free alpha delta Sasaki manifold of negative type with alpha equal -1 and delta equal to 1. And then by homothetic deformations, I get many more and I can realize all parameters alpha and delta I want. Okay, so the upshot is by changing the sign of the metric in the vertical part of a Konishi bundle over a quaternionic Kähler manifold of negative scalar curvature, I get examples in the other class. Okay, now here's the first nice theorem, namely, if we start with 3 alpha delta Sasaki, then we get the generalization of Kashiwada's theorem. The structure is always going to be hypernormal. So all these tensors are integrable. The distribution, the vertical distribution, is integrable with totally geodesic leaves. And delta, now here comes an equation which shows the geometric content of the constant delta. In fact, all the 3 Reb vector fields are killing, and one can compute their commutators. And the commutators are just given by twice delta psi, the remaining Reb vector field. Psi I times psi j is twice delta psi k. So you see that in the degenerate case, the 3 Reb vector fields just commute. And this explains why we normalized the equation exactly that way, so that delta catches this geometric property of the commutator structure. Now, these 2 equations are not to be remembered, but anybody who has done some Sasaki or Fusasaki geometry remembers that there are equations for the Levi-Civita derivative of phi I and for the Levi-Civita derivative of the vector field psi I. Right? And so what I'm just saying with these 2 formulas is that you can compute an analogous curve formula in the 3 alpha delta Sasaki case. It's just that you get more terms which all depend on these factors. Okay, now forget it again. So, but we can compute a lot of the information on the structured tensors we want to have for doing geometry. Now let's go to the second part, namely we want to get some connections, the canonical connection. Now, a metric connection nabla on a Riemannian manifold is said to have skew torsion if the free 0 or 0-free tensor field, which you get by contracting the torsion with an additional vector field, if this tensor is actually a freeform. And remember, this is equivalent, up to parametrizations, to the conditions that this new connection has actually the same geodesics as the Levi-Civita connection. And if you have such a metric connection with skew torsion, you can express the connection immediately through this torsion element, because it's just up to a factor 1/2 the difference between the Levi-Civita connection and the connection you're looking at. Now, a characteristic connection is, in general, if you're given a G structure on a manifold where G is a subgroup of S1, then one asks for connections nabla with skew torsion, preserving the structure. And if such a connection exists, it's called characteristic connection. And we know that many manifolds admit such a connection. And if it exists, it's unique. Almost 20 years ago, Thomas Friedrich and Stefan Ivanov proved that described almost contact metric manifolds admitting metric connections with totally skew symmetric, compatible connections with totally skew torsion, meaning just characteristic connections. Namely, an almost contact metric manifold will have such a characteristic connection, meaning in this particular situation that it makes eta, xi, and phi parallel, if and only if the tensor n phi we introduced earlier is totally skew symmetric. And this explains why I was looking at this condition before, right? If the 3 tensors coming from the 3 Reb vector fields are skew symmetric, is that true for any almost contact structure on the associated sphere? And psi has to be a killing vector field. In particular, this is true for alpha Sasaki manifolds. And the formula for the torsion being a free form, is just as simple as you can imagine, because, I mean, you have a 1-form eta at your hand geometrically, and you have a 2-form, which is d eta at your hand as well. And you wedge the 2 together, and that's your torsion form. You may now say, well, you could have taken phi I, but the eta is proportional to phi I anyway in the Sasaki case. So saying let's try eta wedge phi without the I in the Sasaki case would be just exactly the same. Okay, so we have that, and this torsion, moreover, has a very nice particular new property. It is parallel. So meaning parallel with respect of the connection it defines. Okay. And here comes the first proposition. So by applying the results we had before, if we start with any almost free contact metric manifold, if each of the single structures admits a characteristic connection, then the same holds for every structure in this associated sphere. Now, so you get huge amount of connections, right? Because you get a connection for each single almost contact structure, and we have a whole sphere of them. In particular, we have the three we started with for defining the free contact structure. So it does make sense to ask whether these connections coincide, because that would be then a nice connection we can associate with the three contact manifold. So is it possible to find a metric connection with skew torsion, which is going to parallelize all the structured tensor fields? And the case of a free Sasaki manifold tells us that this is in general not the case, unfortunately. Because if you compute the characteristic connection of each structure for a free Sasaki manifold, then as we just saw, the torsion Ti is going to be eta I wedge the eta I. And then you check quickly that for I not equal to j, these are not the same. And therefore the connections are not the same. So we need to relax our condition that the structure should be parallel, or that all structure tensors should be parallel. And we need some guideline. What would be a good relaxation of these conditions? Yeah? You all with me? Hope so. Okay. Good. And now let me give you, what was the state of the art? We had two examples where we could find by other methods such a connection. And the starting point was to find a generalization of these two main classes of examples. The two classes of examples is that for a 7-dimensional free Sasaki manifold, you can get around. Because for 7-dimensional free Sasaki manifolds, you have compatible G2 structures. And the G2 structure tells you where to look. So you start with a 7-dimensional free Sasaki manifold. And then you take as free form, well, you take the average of the eta I wedge the eta i's plus a term which is proportional to the wedge product eta 1 wedge eta 2 wedge eta 3. Check easily, this defines a co-calibrated G2 structure. Co-calibrated G2 structures always admit characteristic connections, and the torsion is something very beautiful. It's just the sum of the free eta I wedge eta I. This is called the canonical connection of a 7-dimensional free Sasaki manifold, and for good reason, because this connection has beautiful properties. In particular, it preserves the horizontal and the vertical space distribution. It has parallel torsion. It admits a parallel spinor psi, which is called the canonical spinor, and this is automatic because G2 is the stabilizer of a generic spinor in dimension 7. So whenever you have a G2 connection, it automatically gives you for free a parallel spinor. So you take the spinor, and then you realize that if you build the free Clifford products of that spinor with the free Rib vector fields, these are exactly the three Riemannian killing spinors of any free Sasaki manifolds. And remember, on the very first slide, I said that this is equivalent. So looking at this connection allows you to have a spinor, or to find a spinor in a natural way, which actually generates these three Riemannian killing spinors. So this is a good indication. This must be a nice connection. Let's look at the second example, the canonical connection for the quaternionic Heisenberg group. So I take the Heisenberg group as before. And I define first the connection in the following way. It's again the similar summand, but now I take a different constant in front of the wedge product eta 1, 2, 3. Why is it reasonable to take this connection? Because the torsion is parallel and the curvature of that connection is parallel as well. Therefore, this is a naturally reductive homogeneous space, and the connection we found is just the Ambrose-Singer connection from the Ambrose-Singer homogeneity theorem. And the holonomic group is SU2, it acts irreducibly on U and H, and everything is nice. In the 7-dimensional case, right, this turns out actually to be the characteristic connection of, again, a co-calibrated G2 structure. So it has a parallel spin-off field. However, if you've investigated the Quaternionic Heisenberg group before, then you know that the Quaternionic Heisenberg group is never Einstein, whatever you take for lambda, right? So a manifold can admit Riemannian killing spinors if and only if, I mean, it does have to be Einstein in order to admit Riemannian killing spinors. Since I cannot have Riemannian killing spinors here, but I have a parallel spinor field coming from the G2 structure, what can we say about the products psi I times psi? And well, actually, they are generalized killing spinors. A generalized killing spinor is a killing spinor, but with basically the killing constant depending on the direction. So in direction of the same Reeb vector field, then the index, same index here, you get a certain constant. Then if the index here and here is not the same, you get a different constant. And on the horizontal space, you get yet another constant. All right, so we see this connection induces nice spinors and it induces the naturally reductive homogeneous structure. Okay. So can we define a canonical connection for phi alpha delta Sasaki manifolds or some larger class which incorporates these two or which admits these connections at special cases? So we need a weaker condition than nabla phi I equal to 0. We did a very systematic investigation. So the very least condition is what we call phi compatibility, namely connections preserving the splitting, right? We believe that this is a condition we do not want to give up. And the phi i's are not parallel, but they should at least be parallel on the horizontal space. Looking at examples and many other geometric situations, this is a very reasonable condition. Okay. Great. And now there is, if you know something about quaternionic connections, which are in the quaternionic killer case, then there one postulates the following for the Levi-Civita connection, that the derivative, covariant derivative, phi I in direction x is given by some one form and then a linear combination, so the one form evaluated at x, and the linear combination phi j, phi k. So in some sense, you know, the three almost complex structures phi I, j, k are not parallel, but the derivative stays inside the distribution spanned by these three elements. It cannot be anything. It has to stay in this narrow space up to constants which you can compute. You see? Yeah.
Ilka, sorry, in the G2 structures in the previous slides, is it understood when it is torsion free? Is it possible? Or
this one?
The G2 structure, no, attached in general to this Sasakian.
Okay, so it's only in dimension 7. You get a whole family of G2 structures, but some G2 structures make more sense than others. And you want them integrable. So you want them with vanishing torsion.
Yeah, I mean, yeah, torsion free.
Yeah. No.
With holonomy, is it possible or no?
No.
Never.
Not from free Sasaki manifolds. No.
Okay.
But I know only one situation where on the same manifold you get torsion geometry and non-torsion geometry, vanishing torsion geometry. If you look in a very old paper, the only one which I published with Simon Chiossi and with Anafino. Okay, we constructed 7-dimensional manifolds, which is basically a nil manifold times some R. Okay, so this is 7-dimensional. You can see what I write?
Yes.
Good. So on these, you have a geometry with torsion and a G2 geometry with torsion and a G2 geometry without torsion. But this is a clever argument. It does not come from a free Sasaki or anything structure. So if one is interested in examples of that type, then this is the paper to look at. It's very short because it's only the construction of an example.
Okay, thank you.
Right? I don't know any other situations. Okay, so, right. So, as I'm saying, inspired by the Quaternionic case, you would like to have that our connection satisfies such a type equation. One realizes quickly that the only reasonable one forms to choose are eta k and eta j here, and some constant beta, which we haven't yet fixed, which a priori could also be a function. Okay. In particular, if I postulate this equation, this follows automatically because as soon as x is horizontal, eta on x is 0, and therefore I get 0. Good. Wonderful. So now the main theorem about what kind of connections I can have is if I start with an all-three contact metric manifold and I assume I have a metric connection nabla with screw torsion such that for some smooth function I have exactly the condition I required. This is the case if and only if each xi I is killing, all the n phi i's are totally skew-symmetric on H. And for any x, y, z horizontal vector fields, I have an ugly equation. The ugly equation means that I have a certain linear combination of n minus d phi I, n phi I minus d phi I, is just always the same whatever the index is. So this is how you should look at it. For each I, you compute, you write down this quantity, and the three quantities have to be equal. And this beta is what we call a Reb killing function, meaning that you construct a certain tensor Ij, which contains Lie derivatives and other stuff. And again, these three tensors, so you get all tensors for all combinations of indices. On the diagonal, this is 0. And it's antisymmetric. Aij is minus Iji. And it's basically all given by phi k up to a constant beta. Okay, so it's a condition on the killing. It's a killing type condition for the vector fields xi I. And these tensors you can build. This is just what comes out of the computation. So this is the most general case. We just wanted to make sure we don't lose anything by making too restrictive assumptions. If such a connection exists, it's unique, phi compatible, and it's called the canonical connection. And now you can compute the derivatives of all structure tensors phi I, xi I, eta I in terms of the function beta, which appeared in the connection. And you see that you always get something which is basically a linear combination of the same structure tensor. So again, the derivative of each structure tensor is going to be a linear combination of the other structure tensors instead of just being parallel. But we see if beta is equal to 0, then actually all derivatives vanish. So then the characteristic connections of each structure will correspond to the ones of these. And now we say that the normal three contact metric manifold is canonical if all this happens. And if beta is equal to 0, we call it parallel, just because that exactly means that all these structure tensors have vanishing derivative. Now, the canonical connection has nice properties. We get a natural 4 form, just as in the quaternionic case, which is parallel. Eta wedge R1, 2, 3 is also parallel. We can say something about the holonomy. It's inside SPn plus SP1. And for the parallel case, actually, it has to be inside SPn. Good. Okay, and this is how you compute it. That we don't need. Now, going back to phi alpha delta Sasaki manifolds, the upshot is that these are canonical. And this function beta is actually a constant, and beta is just twice delta minus 2 alpha. It should not surprise us that it's 2 alpha and not alpha, because we had seen that for phi Sasaki, which corresponds to delta equal to alpha, the 3 connections were not equal. So we see it's parallel if and only this happens, and we see that parallel case can only appear if it's a positive 3 alpha delta Sasaki manifold. You compute an explicit formula for the torsion, it's parallel, and you recover the examples we had before, 3 Sasaki manifolds and quaternionic Heisenberg groups. You just get the formulas for the torsion I had given in the examples. So we fulfilled our first goal. Now we have a playground to investigate this class and their connections. Right? Now you start doing math as you learned. Here's a little picture trying to summarize up the situation. So it does make sense to figure out this in the alpha delta plane. Then 3 Sasaki manifolds or this single point. We have a line corresponding to 3 alpha Sasaki manifolds. Then the parallel case is given. Yeah, Julius, was this? Bis Viertel vor 1 etwa.
Also noch ein bisschen, oder?
Ja, ja.
Okay, dann gehe ich kurz raus.
Okay, ciao. Sorry, kids. Okay, so you have this plane of these structures. Degenerate corresponds to the X line. We have the parallel case, and actually you can prove that all these classes are not exactly coinciding. You have, for example, here in the parallel case, you have HKT manifolds times a Lie group and other examples. So you get a nice picture summarizing everything up. Okay, the metric cone of a 3 alpha delta Sasaki manifold is hyperkähler with torsion, but I don't want to say something about that. And we also skip the 3 7-dimensional case, because I want to give you some of the outlook. That this is interesting for spin geometry, you can believe me, because this is my daily business. But here's something else which is interesting. In fact, every 3 alpha delta Sasaki manifold has an underlying quaternionic contact structure, just as they're studied by Ivanov, Minchev, Vasilyev since many years. Okay, and you define it by just taking the phi i's restricted to the horizontal space, and the eta i's in the sense of quaternionic contact geometry have to be rescaled. Okay, and so the canonical connection we just constructed, since it preserves this splitting, will have some additional properties, and this turns it into a quaternionic contact connection. And in fact, it's not only that, but the structure you get by this restriction is what is called QC Einstein by them. So 3 alpha delta Sasaki manifolds are a Riemannian analog of QC Einstein manifolds, which do not carry a metric. And this allows to determine the Riemannian-Ricci curvature. So we could recycle their computation to give you a very explicit formula for the Riemannian-Ricci curvature of any 3 alpha delta Sasaki manifold. And this looks complicated, but actually it's not, because it tells you that the Ricci tensor has just block structure, 1 block in the horizontal, 1 vertical block, and in one situation the constant is this, and in the other situation it's this. And similarly, you can also compute the Nabla-Ricci curvature, and qualitatively you get the same. It's also of block structure, 1 constant in horizontal space, another constant in the vertical space, but the numbers are, of course, slightly different. Okay, this is actually a symmetric tensor, which is a consequence of the torsion being parallel. Now, you can ask, okay, when is this a Riemannian-Einstein manifold? There are exactly two situations. If alpha is equal to delta, or alpha and delta are linked by this number, by this relation. Now, this was qualitatively known because it is known that every free Sasaki manifold carries a second Einstein metric by deformation. So this is the deformation. The manifold is Nabla-Einstein if you have this other condition. And it's going to be both Riemannian-Einstein and Nabla-Einstein if you're in dimension 7 and you have this. And this is, in fact, what is known to be a compatible nearly parallel G2 structure. Okay, so we cover all the Einstein metrics that we knew that they should qualitatively exist, but nothing else.
Ilka?
Yeah.
You may also ask, when is a Ricci soliton, right? I mean, when this sum of the eta i's is the Lie derivative of with respect to some field or the Laplace or the gradient of some functional. Have you?
No, we haven't looked at it, but I would be extremely optimistic that it can be done easily. But we haven't done it. But it's
Okay.
it's a good question, actually.
Okay, thanks.
Yeah, that's a good idea. Okay, now here comes the canonical submersion, right? So the theorem is every phi alpha delta Sasaki manifold admits a local Riemannian submersion with totally geodesic fibers satisfying this equation for all horizontal lifts. And this geometry can be viewed as, so I can put it in a setting of a more general result, because Clayton, Moriano, and Zemmelmann they started metric connections with parallel skew torsion. So this is exactly our situation, and reducible holonomy. And our holonomy is reducible because it splits into horizontal and vertical part. So we have a situation where we can apply these results by Clayton, Moriano, Zemmelmann. And one has to check a few conditions to make that work. Actually, we have to prove a slight variation of their proof. So you do a splitting. And, well, you get the following. So suppose that the torsion vanishes when restricted to h times wedge of vertical spires, right? Then this V is the vertical distribution of this Riemannian submersion with totally geodesic leaves, and the horizontal lifts satisfy an equation where this connection nabla sigma is just a metric connection with parallel skew torsion on the base, N. Okay. This is an adaptation from their result because they define things slightly differently, but one just checks that everything goes through to make it fit. The problem is if you stick with their notations, then you do not get the vertical and horizontal space as you're used to them. You get a contribution which wanders around between vertical and horizontal space, and this doesn't make sense. So you have to adapt it this way. And now you prove that for this, now since we know these things, then you have to check the condition. And to check the condition which I gave here, where is it? Yeah, this one. Okay, you have actually to look at the curvature tensor. And you start proving identities for the curvature tensor of such a canonical connection. And these will tell you, yes, this works. And in particular, if beta is equal to 0, this nu will decompose into free trivial one-dimensional representations, which is fine because that's what you expect in a parallel case. And if it's not 0, then you get such a condition. And therefore, the sigma is going to be 0, and therefore the connection on the base is going to be the Levi-Civita connection of the base. And so you get a quaternionic structure on the base, defined by these conditions. And you can compute, for example, the scalar curvature of the base, of this quaternionic scalar base, and you get such a nice equation. Because 16n times n plus 2 is always a positive constant. So if you have a positive free alpha delta Sasaki manifold, right? Alpha times delta positive. This canonical submersion will lead to a quaternionic Kähler base with positive scalar curvature. If it's degenerate, it will have zero scalar curvature, and if it's negative, it will lead negative scalar curvature on the quaternionic Kähler base. So these three classes translate immediately into three very different types of geometry for the quaternionic Kähler base. This explains once again why this is a good scheme for dividing these manifolds. Let's say something about the homogeneous case. So we know now that for a homogeneous free alpha delta Sasaki manifold, we will get a projection of a homogeneous quaternionic Kähler space. And if delta is not zero, then the base has non-vanishing scalar curvature. Now, what do we know about quaternionic Kähler manifolds, homogeneous ones? So there are basically two situations. Either you have a compact quaternionic Kähler symmetric space, a so-called Wolf space, or one of the non-compact duals with negative scalar curvature, or you have a so-called Alexievsky space, which is a quaternionic Kähler homogeneous space with negative scalar curvature and a transitive solvable group of isometries. Some of them are symmetric, but not all. So symmetric Alexievsky spaces exist, but non-symmetric as well. So we have here a dichotomy, right? For positive scalar curvature, such a homogeneous space has to be symmetric. For negative, it doesn't. How can we adapt this to, or how can we use this to learn something about homogeneous free alpha delta Sasaki manifolds? Now, let me quickly recall, and I see that I'm starting to go over time now. So you tell me when I should have finished, okay? And as long as you don't cut the connection, I will continue talking. So, Boyer-Galitsky-Mann classified homogeneous free Sasaki manifolds, proving that you have one for each simple compact Lie group. SPN, well, this is up to covering, SU, SO, G2, F4, etc. They're all simply connected except for projective space. And due to Draper, Ortega, and Palomo, we have a very nice uniform description of all the simply connected homogeneous free Sasaki manifolds in terms of free Sasakian data. So we generalize this in the following way. A generalized free Sasakian data is a triple such that G is a real simple group. And this is it had to be compact in the first approach. We have this ordering of subgroups. And the Lie algebras of these three Lie groups satisfy G, G naught forms a symmetric pair. G naught is equal to H plus an SP1 factor where SP1 and H commute as subalgebras. The complexification of G1 can be written as C2 times W for some HC module of dimension 2n. And I let H, SP1, and G1, and more precisely their complexifications, act by the natural actions on W and C2. And this model contains in particular some compact symmetric pair and the non-compact symmetric duals. So this is how one should memorize all this, okay? M is going to be a reductive complement for the quotient G over H. So here I have my big G, H plus SP1 plus G1. H plus SP1 yield G naught. SP1 plus G1 yield M. And this is my local model for the vertical space and the horizontal space. Okay? And whenever you have this, then the theorem is, if you start with such data, take two constants alpha delta in R and assume that G is compact for alpha delta positive and non-compact for alpha delta negative. Then on the quotient G over H, you define a J-invariant structure with the following tensors. The metric on SP1 is given by the kappa is the killing form. This multiple of the killing form on G1 you take another multiple of the killing form, and of course SP1 and G1 should be orthogonal. This is what you have to take for the Rep vector fields, the eta i's, the phi i's. So this is basically ad psi I, right? And this is then a homogeneous phi alpha delta Sasaki manifold, fibering over the symmetric quaternionic space G over G naught. And conversely, every simply connected homogeneous phi alpha delta Sasaki manifold fibering over a symmetric space is obtained by this construction. So we get a straightforward generalization of the work by Draper et al., which I guess fits very nicely in this context. What about the non-symmetric case? Okay, here's the list you get. Don't need that. So it took us tremendous amount of time, but so if you have ever looked at the papers of Alexievsky and later Vicente Cortés on these non-symmetric Alexievsky spaces, you will remember that the construction is really far from trivial. Okay, so I give no details at all, but just state the result that if you start with a non-symmetric Alexievsky space, we were able to construct homogeneous negative phi alpha delta Sasaki spaces over them. Therefore, there really exist negative homogeneous phi alpha delta Sasaki over non-symmetric base. So this is very nice because now you get a whole new class of manifolds. Let me, if you have like 2 or 3 minutes, I will give you a very slight idea about the other application, because I believe this is something people might be interested in for other, totally other questions, namely curvature operators. So the Riemannian curvature, we know that it is a symmetric operator on 2 forms, right? Now, if a connection, metric connection with skew torsion has parallel torsion, then the curvature of this connection with torsion is again a symmetric operator. Okay. Now, if we look at our canonical submersion, then we can relate the curvature operator on the big manifold to the curvature operator of the base, and we have control over the difference term. Good. And moreover, the curvature of the quaternionic Keller base can be computed explicitly in terms of the structure tensors of the manifold. And now I will say in a minute why we started doing that. Now we constructed eigenforms for the curvature operator in huge quantity. For example, the curvature operator of the canonical connection has as orthogonal eigenforms these linearly independent combinations of the fundamental forms and the corresponding wedge products. And we can decompose the curvature operator in the following way. The Riemannian curvature operator equals the canonical curvature operator plus 2 extra terms, 1/4 G plus 1/4 sigma T. 1/4 sigma T is a 4 form, which is basically dt. All right, T is a 3 form, dt is a 4 form, so this is where sigma T comes from. And GT is basically a symmetric version of the torsion, because it's just the metric and then enter T into arguments. So we have a nice formula relating the Riemannian and the Nabla curvature operators, and we have eigenforms. And so we go from the eigenforms of the Nabla curvature operator to eigenforms of the Riemannian curvature operator. All right? Namely, we investigated when the forms found above are also eigenforms of the Riemannian curvature operator. And it appears that this is actually true if and only if the manifold is Einstein. And in the other cases, we give the equation, but then it's a linear combination. So if you need eigenforms of the curvature operator, it doesn't matter which one, that's where to look. then let me give you in a few minutes what is positive, strongly positive curvature. For a two-plane, we know, I will show you the whole page, that the sectional curvature can be computed just as Rg sigma times sigma. So if the curvature operator is positive, then I can conclude that I have positive sectional curvature. A manifold is said to have strongly positive curvature in the sense of Thorpe if there exists a four-form omega such that Rg plus omega is a positive definite operator. This implies in particular immediately that you have positive sectional curvature. So we have the following inclusions or implications. If Rg is positive, that means strongly positive curvature, then I have positive sectional curvature, and the same for larger or equal to 0. And so in fact, we investigated when this is the case for phi alpha delta Sasaki, and here comes the motivation. On a phi alpha delta Sasaki manifold, I can control all these terms. Because I will, if you look at it, you see that this sigma t appears here. Okay, so the manifold is going to have strongly non-negative curvature with respect to this particular four form. So remember, in the definition here I have any omega. But now I take the free form which comes from the geometry, the sigma t. And so it's going to be strongly non-negative with this four form if and only if this is non-negative. Now GT is always non-negative, so we have to look just at this. And we realize, well, this is the case basically if alpha times delta is positive. If a positive phi alpha delta, R is going to be positive if and only if alpha times beta is larger or equal 0. Okay. And so a positive homogeneous phi alpha delta Sasaki manifold is strongly non-negative with this particular four form if and only if alpha times beta is larger or equal to 0. Now this beta, remember, it was alpha minus 2 delta. Okay. Now, homogeneous manifolds with strictly positive sectional curvature, we know them. They have been classified. And in dimension, the only ones which admit homogeneous phi alpha delta Sasaki structures are the Alov-Wallach space and the sphere. So these, we know, should be strongly positive. And in fact, there's this nice work by Betziol and don't remember the name of the second one, which looked at these spaces.
Ricardo Mendes? Ricardo Mendes.
Ricardo Mendes, thank you. Yes. So these spaces are known to be strongly positive. The point is, in this theorem, that we can now say explicitly for which four form. Because if strongly positive is a reasonable notion, and I will believe that it is a reasonable notion, then it should not be happening for any four form. It should become happening for a four form which is induced by the geometry. And for any connection with skew torsion, the only four form which comes immediately to your mind as a reasonable four form is this sigma t, because it's just dt. And it plays a huge role in connections with skew torsion. So the whole upshot is that we prove that indeed this works well in the known examples with the four form, which you would guess is the right one to look at, with the factor minus 1/4. Okay, and if you want it non-negative, and if you want it strictly positive, you have to deform with a little epsilon. So this is, and here's a certain multiple again to be taken. So what we say is that strongly positive with this four form, the four form to look at is sigma t, whatever your connection is. Okay, I went well over time. Thank you very much for your patience and listening, and hope you're not falling asleep. That's it.
Thank you very much, Ilka, for the beautiful talk. Is there any question or comment for Ilka?
Yes, I have one more question. So in the compact case, when you show this generalized data,
Yes.
can you show the table that I mean, G over H is not a symmetric space, right?
No, in this generalized data, it's always no. The base is symmetric. Oops, here we are.
G over H is symmetric?
No.
No.
No, G over
So
H is the total space. What is
Okay.
symmetric is G over G naught.
Okay. But then these Einstein metrics, you get Einstein metrics in the previous page.
Yes.
When lambda delta is equal to alpha.
Right.
Are these new Einstein metrics? I mean, are they known?
No, they're not new. No.
Uh-huh.
They are known because you had a very general deformation argument. Whenever you have, you see, phi alpha delta Sasaki manifolds don't need to be homogeneous, right? So you have an Einstein metric in exactly two situations, when it's phi alpha Sasaki or when the alpha and delta satisfy this equation. But it was known before that any phi Sasaki manifold, the phi Sasaki metric, admits a deformation, which is again Einstein. And so this alpha delta basically implement in a very explicit way this deformation. Right?
I see.
So it proves that there are no other such no other Einstein metrics, which was not known before, but also in the homogeneous case. Since you had the general theorem, I don't know whether the parameter, or I believe that the parameters were not described as explicitly as we did it here, right? Because if you look in this description, I mean, this is as explicit for the metric as you can have it.
Yeah.
Right? So these formulas maybe were not known in the most general situation so that you can really work with it. In particular, this abstract deformation was not quantitative. It was just that there exists a deformation such that. Right?
Okay.
But we recover, in principle, known elements, but we give a much simpler description and a uniform description. This is what I would explain in this context.
So these examples, I mean, do you know a compact examples with delta 0 in Degenerate?
I don't think so. No.
Oh.
So in the original, so we haven't looked at them recently. We have some examples, but not very bright examples. In the paper with Giulia Di Leo, the very first one. And since then, we did not think about it again. Leander told me that he was trying to think about them. Once he will have his PhD defense, like in 2 weeks. But nothing very serious.
Okay, very nice talk. Thank you.
Thank you also. Now let me go on a page where I have some space. Here comes the advertisement. So there are 2 events next year, and you're all invited to come, and I hope that you will be able to come. So one is, we are organizing a session of the seminar Sophusli in Norway. Okay, so this is, I mean, Sophusli being Norwegian, this is the very first time that we do it in Norway. So organizers is me, together with Boris Kruglikov and Joachim Hilgert. You may know these names. And it's going to be in June. I think it was June 12th to 19th. And we have very generous funding by the Norwegian government. So there will be some travel grants available. This has been postponed several times. You can guess the story. You might have heard about it. And we are going to send out an email to the Sophusli mailing list. I don't know. Is anybody on this Sophusli mailing list of you? Maybe. So they exist. So
No.
the German...
No.
No, I don't know.
No.
No.
Which city?
Well, Norway, the little village of North Fjorddate, where Zofusli was born.
Oh.
They have a conference center there.
What's the name?
North Fjorddate. Go to my webpage and then you click the link. This is the easiest. Okay. I updated the page today. Okay. And if you go to, so the Seminar Zofusli is a recurrent meeting. Normally it was twice a year, but now there has been a break of almost 2 years. And this is going to be the restart. And this originated as a series of, half-year meetings of anything related to leaf theory, be it geometry, harmonic analysis, in Germany and adjacent countries. This was founded 1990, so it's now 30 years ago. And now it has become an international event, right? And Boris Kruglikov suggested to have it for the very first time in Norway. So have a look, and it's a beautiful place. It's a village with 3,000 inhabitants, right? So this is the first event. The second is, we don't know yet what the title is going to be, but at the moment what we are looking at, the title is maybe something like Symmetries, Structures, and Spaces, okay? So we wanted to make something more interesting than the usual special structures on Riemannian manifolds. So we were playing around with names this morning. So something like Symmetry, Structures, and Spaces might be the title. And this is going to be in Bari. So the people like Giulia Di Leo, Antonio De Lotta are main organizers in Bari. And this is going to be, now I have to check the week, which joins the last days of August to the first days in September. If any of you has a calendar and is faster than me, then I will tell you 2021, this is wrong, 2022. This is 29th of August until 3rd of September, right? So Di Leo, Lotta, and all these people are main organizers. And again, you're all welcome. And in particular, if any of you is planning to travel to Europe or Germany for a longer time, keep in mind whether these dates maybe can be combined with some of your other plans. That's the main reason why I'm giving them to you right now, because obviously coming only for a week is rather stressful. So maybe you can combine it with something which gives a nice trip. Right? That's.
Thank you. Thank you very much, Ilka. And please thank again Ilka for her talk.
Thank you all.